Today we're going to talk about the energy of a simple harmonic oscillator. And in this case, we know that the total energy of a system is equal to the kinetic energy plus the potential energy U. And our kinetic energy in this case is 1 over 2 mv squared. And our potential energy in this case, well, what is the potential energy when you stretch a spring? Well, now imagine we have a string and we let it stretch through a small distance, which we call dx, right? The work done in stretching the spring through a distance dx is, so dw is equal to f dx. So this is the work done in stretching the spring in a little distance, because the formula for the work is the force times the distance. So in this case, if we integrate this, if we integrate both of them, this is going to give, because if we integrate dw, then that just gives us w, right? That's give us the work. So if we integrate our f dx, let's say starting from x equal to 0 to some arbitrary point x, what is this going to be? Well, let's remind ourselves is that f is essentially equal to kx. So if we change the expression, so this now becomes kx dx. Well, what do we do here? Well, we take k out, of course, because k is a constant. So k is equal to integration from 0 to x dx. And for this inside part, let's write this again. Actually, if you know the power rule, x to the power of 1, not the power rule, but the reverse power rule for integration, if you know that, if you integrate this, you'll get something like x to the power of 2 over 2, right? And then we integrate from 0 to x plus c, of course. Then this is going to give us, well, in our first case is k times x squared 0 squared over 2 plus x squared over 2. So this is obviously k times x squared over 2, which is 1 over 2 kx squared, right? So this is going to be our potential energy for the spring, right? So let's jump back to our original equation. So we have the total energy is equal to 1 over 2 mv squared, which is our kinetic energy k, plus our spring potential energy, which is 1 over 2 kx squared, which is our u. And then as you learned in my last video, where I talk about the general solution to a differential, to a simple harmonic motion, is that our x function, so x is equal to, our displacement is equal to a cos omega t plus phi. And our velocity, of course, is that if we take derivative of dx, it's going to be, let's see here, so negative omega a sine omega t plus phi. So this is going to be our v. So if you look back into this equation, right, you can kind of plug the x in it, and also you can kind of plug the v in it. So let's do that. So E is equal to 1 over 2 m v squared. So that's omega squared a squared sine squared mu omega t plus phi. And then this plus our potential energy, which is 1 over 2 k, we have just a squared cos squared omega t plus phi. And then to particularly in this expression, remember our omega from my last video, we know that this is actually equal to k over m. So if we make that, if we kind of replace this with k over m, you'll notice that the m and the m cancel out. So this actually just becomes 1 over 2 k a squared sine squared omega t plus phi plus 1 over 2 k a squared cos squared omega t plus phi. And as you learn in the grade 11, you could kind of just take them out, right? Because they both have 1 over 2 ka squared. So we take this out, and then this inside becomes sine squared omega t plus phi plus cos squared omega t plus phi, which this by the trigger identity is equal to 1. So our total energy in the system is actually 1 over 2 Ka squared. This is pretty obvious, where A is the amplitude, of course. This is actually pretty intuitive because this says that the energy of this harmonic oscillator is proportional to the square of the amplitude of the oscillation. So what this means is that A is what we initially extend the spring, right? So the more we extend the spring initially, it's going to have more potential energy. That's pretty intuitive. It's like saying that if we have a spring that's that's in equilibrium position, if you play with those toy spring, you stretch it by like a little bit, it's going to oscillate a little bit. But if you stretch it by a lot, there's right, if you have a bigger displacement for your initial stretch, right, you're going to have more energy in the system. So it's pretty intuitive. So the graph of the total energy is going to look like something like this. So I'm going to draw, so this 0, so where the y-axis is energy and our x-axis is just going to be t. So something's going to be like this. So our potential energy goes down, and then it goes up, and it goes down, it goes up, where our kinetic energy goes up, and it goes down, and it goes up, and it goes down, right? And then remember, if we draw like a dotted line right here, this represents the total energy, which is the U plus K. This is never exceeded, right? Because you don't see a scenario where you stretch the spring for let's say 5 centimeter and it oscillates and jumps to 6 centimeter, right? That violates the conservation of energy. So obviously the peak, which is the amplitude where you started from, right, is always the same. So as you can see, I'm going to use red pen. As the potential energy goes down, our kinetic energy rises up, and then when potential energy is equal to 0, we have the maximum kinetic energy. And then the same happens as the kinetic energy goes down, the potential energy goes up. So it's just a repeat cycle like this between, the energy is always shifting between the kinetic and the potential, but the constant, the total stays the same, as both of these peaks never passes the top of this. So this would just be the energy of a simple harmonic oscillator, and I hope you have learned something.